Before sunrise on Lake Superior, a train begins to disappear into a dock. Car after car rolls over a system of pockets, gates, and conveyors. What looks like a line of ordinary freight cars is carrying processed iron ore, small dense pellets made from rock mined across northern Minnesota. The train does not pull alongside a warehouse. It feeds a machine built into the shoreline. Below it, a Great Lakes freighter waits with its cargo holds open. American Steamship Company says vessels in its self-unloading fleet can carry from 24,000 to 81,000 gross tons on one trip. The American Spirit has a midsummer deadweight capacity of 62,400 gross tons. So a thumbnail might say 66,000 tons, but not every ship carries that amount. The point is the scale of one departure, and this is only the beginning of the trip. The pellets came from the Iron Range. Rail carried them toward Lake Superior. The dock is loading them into a vessel built for a freshwater industrial network. That vessel may pass through the Soo Locks, cross several lakes, and discharge its cargo beside a steelmaking complex hundreds of miles away. The final products can enter automotive, appliance, construction, distribution, and pipe markets. Yet the supply chain operates far from coastal container ports, behind long ore docks, aboard ships that rarely leave the Great Lakes. This film follows that chain from beginning to end, not as a story about one heroic ship, and not as a prediction that one delay will shut down America. It is a story about a system. Mines, trains, docks, vessels, locks, icebreakers, maintenance crews, and steel plants, all handing the same material from one specialized machine to the next. The cargo begins as taconite, a hard rock containing iron minerals. Mining companies crush and process that rock, separate the iron-bearing material, and form it into pellets that can travel through a bulk handling system. By the time the pellets reach the waterfront, they are no longer an irregular pile of stone. They are a standardized industrial feedstock designed to flow through rail cars, chutes, ship holds, and blast furnace supply chains. Northern Minnesota has several active Lake Superior gateways for this trade. Duluth Superior, Two Harbors, and Silver Bay connect the Iron Range to the water. The Minnesota Department of Transportation describes roughly 12 to 14 dedicated ore trains moving each day in the region covered by its District 1 freight plan. Those trains carry taconite toward the docks, rather than toward a single universal destination. There are parallel chains across the system. CN describes pellets moving from Minnesota mines to Duluth and Two Harbors for shipment toward the lower lakes. Cleveland Cliffs describes North Shore material traveling about 47 miles by rail from near Babbitt to Silver Bay. For this film, one route gives us a concrete thread to follow. At Hibbing Taconite, an open-pit mine and concentrator produce magnetite concentrate. An on-site plant turns that concentrate into pellets. Rail then carries the pellets to a ship-loading port in Superior, Wisconsin. From there, Cleveland Cliffs says the cargo is shipped to its Burns Harbor steelmaking facility in Indiana. That does not mean every pellet from Minnesota goes to Burns Harbor. It means this is one documented path through a much larger network. The mines sit inland. The receiving steel plants sit around the lower Great Lakes and beyond. Rail gathers material at concentrated loading points. Ships carry it across a water system whose channels, weather, and lock dimensions shape the vessels themselves. Neither mode replaces the other. The train is not competing with the vessel for the entire journey. It is feeding it. That is the first lesson of this supply chain. Its strength comes from specialization. It also means that every transfer point has a job no other part performs in exactly the same way. An ore dock can look almost motionless from a distance. A long structure extends over the water. Rail cars gather above it. A ship lies against the wall. But inside that shape, the cargo is changing direction several times. The train must arrive in the correct sequence. Cars move through the unloading system, gates open, pellets fall into storage pockets or onto conveyors. From there, chutes and belts direct the material into selected cargo holds. Loading a bulk ship is not simply a matter of filling the nearest empty space. The vessel has to remain within safe operating limits as tens of thousands of tons accumulate. Cargo is distributed among multiple holds, and the dock and ship coordinate the sequence. The exact plan can vary by vessel, dock, cargo, and destination, so it would be misleading to invent one universal loading formula. What is constant is the need for coordination. A rail schedule feeds a dock schedule and meets a vessel arrival. The vessel needs a usable berth, available cargo, working machinery, and a plan for which hold receives the next stream. This is why the dock is better understood as a machine than as a parking place. In the 2025 season, Duluth Superior handled 25.3 million short tons of total waterborne cargo. Iron ore accounted for 16.5 million tons of that total. Those numbers describe one port complex, not the entire Great Lakes fleet and not the whole Great Lakes seaway system. But they show the scale passing through a limited number of physical terminals. The workers manage flow, timing, position, machinery, and safe transfer. A delay upstream can leave a ship waiting. A dock problem can leave a train standing. A late vessel can disrupt the order of cargo and berths. Coordination does not automatically mean fragility. Ports have multiple facilities, operators schedule around maintenance and weather, and different docks serve different routes. But high-volume logistics still depend on synchronized processes. Once the holds are loaded and secured, the dock releases the vessel into the next machine, the Great Lakes navigation system itself. Great Lakes freighters are often called Lakers. The name sounds simple, but the fleet is not one uniform class of ship. Some vessels are hundreds of feet shorter than the largest ships. Some carry iron ore, while others carry limestone, coal, grain, salt, cement, or other dry bulk cargoes. Not every Laker is a 1,000-footer, and not every trip serves a steel mill. But the largest vessels reveal how closely ship design follows the waterway. The American Spirit is one example. It is 1,004 feet long and 105 feet wide. Its beam fits within the 110-foot width of the Po lock, with limited room to spare. Its long, low profile spreads cargo across multiple holds while respecting the draft and dimensional constraints of Great Lakes routes. The ship is also a self-unloader. That changes what happens at the destination. Instead of depending entirely on the large shoreside crane or bucket system, the vessel carries its own network of conveyors and a deck-mounted unloading boom. The ship is both transport system and mobile bulk handling plant. American Steamship Company says its current self-unloading fleet ranges from 635 to 1,000 feet. During the navigation season, the vessels operate around the clock. The company lists single-trip carrying capacities from 24,000 to 81,000 gross tons, and unloading rates from 7,000 to 10,000 net tons per hour. Those are company fleet ranges, not universal statistics for every Great Lakes vessel. A 1,000-foot Laker is not an ocean container ship trapped inland. It is optimized for lock dimensions, channels, freshwater drafts, dense cargo, and fast transfer between specialized ports. Freshwater also changes the voyage. The ship crosses inland seas, but it remains inside a connected chain of lakes and rivers. It passes navigation channels maintained for commercial traffic. It approaches bridges, turns, docks, and locks on routes where local knowledge and precise vessel handling matter. From the wheelhouse, the scale reverses. A ship that looked enormous at the loading dock becomes one moving object inside a larger system of water levels, traffic, weather, and infrastructure. and every vessel carrying ore from Lake Superior toward the lower lakes eventually reaches the same geographic hinge, the St. Mary's River at Sault Ste. Marie. Lake Superior sits about 21 feet above the lower Great Lakes. A loaded freighter cannot simply sail down that drop. It needs a controlled descent. The Soo Locks provide it. A vessel approaches the lock complex through the St. Mary's River. Operators assign a chamber. The ship enters slowly, guided by instructions, lines, and the geometry of the lock. Gates close behind it. Water leaves the chamber until the vessel reaches the lower level. The downstream gates open and the ship continues toward Lakes Huron, Michigan, and Erie. For an upbound vessel, the sequence runs in reverse. The chamber fills and lifts the ship toward Lake Superior. USACE says crews complete more than 7,000 lockages during a 42-week navigation season, operating 24 hours a day, 7 days a week. A 2026 USACE release describes more than 4,500 vessels carrying up to 80 million tons of cargo through the locks annually. Iron ore is one major cargo among coal, wheat, limestone, and others. The complex currently relies on 2 operating commercial locks of very different sizes. The Po lock is 1,200 feet long and 110 feet wide. The MacArthur lock is 800 feet long and narrower. The difference is not cosmetic. Many modern lakers are too large for MacArthur. USACE states that 88% of the iron ore moving through the Soo Locks is restricted to Po because of vessel size. The Soo Locks do not carry all American freight. They do not serve every steel mill. A temporary delay does not instantly stop national manufacturing. At the same time, USACE says nearly all domestic U.S. iron ore passes through this location. For the large vessels that dominate that movement, Po provides the usable chamber. That concentration creates an operational hinge. It also explains decades of maintenance and investment. The Po lock opened in the late 1960s. Crews inspect and renew gates, concrete, hydraulic and electrical systems, ship arresters, and other components. Reliability is produced by maintenance. It is not a permanent property of concrete and steel. USACE is also building a new lock designed to match Po's 1,200 by 110-foot dimensions. As of July 2026, USACE schedules completion for summer 2030. The meaning of the project is redundancy. A second Po-sized chamber would give the system another route for vessels that cannot fit MacArthur. The project is not evidence that failure is imminent. It is a response to concentration risk in an aging system. Every successful passage preserves the schedule downstream. A queue is not automatically a crisis, but it consumes time in a chain built around continuous movement. Once the ship clears the St. Mary's River, the physical bottleneck is behind it. The next challenge is turning a vessel full of ore back into a controlled stream of material. At the receiving port, the vessel does not need to be emptied one bucket at a time. Inside a self-unloader, the cargo holds are sloped like hoppers. Gates at the bottom release pellets onto tunnel conveyor belts running beneath the holds. Those belts carry the material toward one end of the vessel. From there, a loop or incline conveyor lifts the cargo to the main deck. The material transfers again, this time onto the long boom conveyor visible above the ship. Hydraulic machinery raises and swings the boom until its discharge end sits over the correct place on shore. Then the ship becomes a moving factory. Pellets travel out of the holds, below deck, upward, across the boom, and onto a stockpile or into a receiving hopper. The unloading boom can reposition the stream as the pile grows. The vessel gradually rises in the water as tens of thousands of tons leave its holds. American Steamship Company says its self-unloaders can discharge without shoreside unloading equipment or shoreside personnel operating a separate unloading system.
Its largest stated discharge rates reach 10,000 tons per hour. Again, that is an operator maximum, not a promise that every cargo leaves every ship at the same speed. The dock still needs adequate depth, mooring space, and somewhere for the cargo to go. But the ship brings the principal discharge machinery with it. That flexibility helps explain why the technology spread across Great Lakes bulk shipping. A vessel can load at one specialized ore dock and unload at a receiving facility designed around stockpiles, hoppers, conveyors, rail, or direct industrial use. The unloading sequence also completes a circle. At the origin, shore machinery filled the vessel. At the destination, the vessel's own machinery empties it. In both places, gravity and conveyors turn a static pile into a controlled flow. The cargo is still not steel, but it has reached the industrial customer that can transform it. For our documented case, that customer is Burns Harbor on the southern shore of Lake Michigan.
Cleveland Cliffs describes Burns Harbor as a fully integrated steelmaking facility. That phrase means several stages of production exist within one industrial complex: iron producing, steel producing, casting, hot rolling, cold rolling, finishing, and coating. The plant operates 2 blast furnaces and has the capacity to produce nearly 5 million net tons of raw steel annually. Capacity is not the same as actual annual output. It describes what the facility is configured to produce. Our case study pellets arrive from Hibbing Taconite through Superior. At Burns Harbor, they enter a much larger recipe of raw materials, energy, equipment, and labor. Ironmaking transforms iron-bearing feedstock. Steelmaking adjusts the material into controlled grades. Rolling reduces thick steel into sheet or plate. Finishing lines alter surfaces and properties for particular customers.
The products listed for Burns Harbor include hot-rolled sheet, cold-rolled sheet, galvanized sheet, and heat-treated plate. The company identifies automotive, appliance, construction, distribution, converter, and pipe and tube markets among the customers served. A car, refrigerator, building component, or pipe cannot be traced to this vessel merely because Burns Harbor serves those markets. Steel supply chains mix material across facilities, product lines, and customers. The accurate claim is narrower and still powerful. Great Lakes iron ore logistics feed integrated steelmaking capacity that supplies major American industries.
The system also extends beyond one company. In 2025, U.S. flag Great Lakes freighters carried 71.3 million tons of cargo. Within that fleet total, 39.1 million tons were iron ore. A separate measure of iron ore shipments from Great Lakes ports was 43.4 million tons. Those figures describe different scopes and should never be merged, but both show that ore remains central to the region's waterborne economy. The wider binational Great Lakes Seaway Corridor moves more than 160 million metric tons in a typical year through more than 100 ports and commercial docks. A study associated that activity with roughly $50 billion and 356,858 U.S. and Canadian jobs. Those are corridor-wide estimates, not Soo Locks or iron ore figures. At the scale of one cargo, the process feels simpler. Pellets leave a ship, stockpiles grow, conveyors carry material inland, the vessel finishes unloading and prepares for another assignment. But the receiving mill is planning beyond one arrival. It needs a reliable flow across a season shaped by weather and a scheduled winter closure. That means time itself becomes part of the infrastructure. Great Lakes shipping does not operate on an identical calendar to a warm water port. Federal regulation sets the Soo Locks operating season around the feasibility of vessel movement under typical ice conditions. The major annual closure runs from January 15th to March 25th. During that period, commercial traffic through Po stops, and maintenance crews take over the lock. This is planned seasonality, not a surprise shutdown. Crews use the closure to inspect and repair aging infrastructure. Depending on the year's work, they may dewater a chamber, clean areas below the normal water line, inspect manholes, repair gates or concrete, service hydraulic and electrical systems, and prepare the lock for another navigation season. The work is compressed into roughly 10 winter weeks. Cold, snow, ice, and limited access make the schedule difficult.
Yet the closure also creates an opportunity unavailable during continuous vessel traffic. A chamber that normally moves ships becomes a construction and maintenance site. Outside the lock walls, ice creates a different operational problem. Operation Taconite is the Coast Guard's largest domestic icebreaking operation. Its purpose includes supporting safe movement of taconite from the head of the lakes toward steel mills on Lakes Michigan and Erie. Icebreakers maintain tracks, assist vessels, and help preserve access through critical waterways when conditions restrict navigation. The nationwide domestic icebreaking total for the severe 2025 to 2026 season was about 6,940 hours from more than 30 Coast Guard cutters and boats, assisting or enabling 981 vessel transits. That is a national figure spanning several regions, not a Great Lakes-only total. For this film, the important fact is operational rather than statistical. Ice is not merely dramatic weather around a ship. It changes resistance, maneuvering, channel availability, navigation aids, and the need for coordinated assistance. The shipping season, therefore, has two connected forms of maintenance. Crews maintain vessels and locks during the closure. Icebreaking crews maintain navigable paths during winter operations at the edges of the season. The calendar is not an external inconvenience. It is built into inventory, scheduling, repair, and industrial planning. That makes the system disciplined. It does not make it immune to delay. Chokepoint stories often jump from normal operation directly to national collapse. Real logistics usually move through smaller steps first. Start at the mine or railroad. If one loading stream is interrupted, cargo can wait, schedules can shift, and another facility may absorb part of the pressure if routes and contracts allow. The result is delay and reduced flexibility, not an automatic shutdown of every mill. At the dock, a conveyor or berth problem can hold both trains and ships. The effect depends on duration, available inventory, alternate terminals, vessel schedules, and the exact customer waiting downstream. On the lake, wind, visibility, ice, and channel conditions can slow movement. Coast Guard assistance can preserve access, but an escort or maintained track does not eliminate weather. A late arrival consumes time that may have been reserved for another loading or unloading slot. At the Soo Locks, a short outage creates a queue. In October 2018, USACE took the Po lock out of service for a planned repair to critical gate components. The work lasted about 9 hours. 3 vessels waited roughly 8 hours. That event did not stop American steelmaking. It shows the first-order consequence clearly. Ships wait while the clock continues moving. A prolonged Po outage is a different category because vessel size limits the available alternative. USACE says 88% of the iron ore moving through the locks is restricted to Po. Its planning material also says existing rail and truck infrastructure cannot simply absorb the enormous commodity volume that would need to bypass the lock. That does not justify attaching an old, worst-case GDP number or predicting a precise number of jobs lost. Those models depend on assumptions about inventories, duration, industrial responses, and the wider economy. This film does not use them. The defensible conclusion is structural. A long interruption at Po
would constrain large vessel movement in a supply chain built around waterborne scale. Mines, docks, vessels, and mills would respond, but their alternatives would not recreate the same capacity overnight. This is why redundancy matters. The new lock is designed to give Poe-sized vessels another chamber, allowing one large lock to undergo work without concentrating all suitable traffic in the other. Resilience is not the absence of delays. It is the presence of maintenance, inventory, alternate facilities, operating procedures, and eventually redundant infrastructure that keep a delay from becoming something larger. The chain also has fixed geography. The mine cannot move to the mill. Lake Superior cannot be lowered to Lake Huron. A 1,000-foot ship cannot squeeze through an 800-foot chamber. The system works by respecting those constraints and scheduling around them. By the time a finished steel product reaches a highway, appliance plant, construction site, distributor, or pipe manufacturer, the Great Lakes voyage has disappeared from view. The pellets are no longer pellets. The train has returned for another load. The vessel has left the receiving dock. The lock is preparing for another passage. That invisibility is part of what makes infrastructure easy to underestimate. The ships are impressive, but their size is not the real story. The story is coordination across specialized systems. Mines make a consistent feedstock. Railroads concentrate it at the water. Docks transfer it at industrial scale. Lakers carry it through a freshwater network. The Soo Locks manage a 21-foot change in elevation. Self-unloading machinery turns a ship back into a flowing supply line. Steel mills transform the cargo into material for other industries.
Winter does not pause the system accidentally. It divides the year into navigation, icebreaking, stock management, and maintenance. Reliability comes from people inspecting gates, repairing vessels, clearing channels, scheduling trains, positioning booms, and adapting when one link slows. None of that means every American steel mill depends on one ship or one dock. It means a significant part of domestic iron ore movement relies on an inland transportation network built over generations and renewed one component at a time. The Great Lakes can look like open water between distant shorelines. For the steel supply chain, they are something more precise, a working industrial corridor. And the vessels crossing them are not scenery. They are moving parts in the machine that keeps American steelmaking supplied.